Welcome pre-cal students to class today on this Tuesday the 8th. Hope you guys are doing well. Hope you're ready to learn some math today. Let's go over these announcements very quickly. There will be no quiz this Saturday. If I did give you a quiz, you would have to turn it in on Tuesday the 15th, and that's right in the middle of spring break. And so let's have no quiz this coming Saturday. I'm sure you guys will enjoy that. So your last day of class before spring break will be this Friday, which would be the 11th, I believe. I think that's right. That's your last day of class, and then you'll have this whole week off, Monday through Friday, and then your first video will be again on April 21st, I believe. I'll check on that in the next video I make for Wednesday of this week. I'll have some more information, but let's go over this again. No quiz this Saturday, so good news for you guys. Spring break will be the 14th through the 18th, and your last video to watch then will be this Friday the 11th, and I think the next one would be April 21st, which is a Monday, I'm pretty sure. Your tests are due by Wednesday. It was good to see you guys yesterday, and your tests are due by Wednesday. And then stay on top of your integrity sheets, okay? Stay on top of your integrity sheets, make sure they're all caught up so you do not have to do a lot of homework all at one time. Okay, let's go ahead and get started with today's notes. We are building up to something. We are building up or getting ready to graph rational functions, okay? That's our goal from this lesson. Before we do that, though, we need to look at some characteristics of the graphs of rational functions. And then tomorrow, Wednesday, we will start graphing them, okay? But today we're just going to look at some characteristics of rational functions. Your heading today is called Asymptotes of Rational Functions. Asymptotes of Rational Functions, lesson 3.5. And the date today, if you like to keep track of that, is the 8th of April, okay? 4/8. Let's first of all look at what a rational function is, okay? A rational function exists when you have a polynomial function over another polynomial function. And here's an example. Notice I have x minus 3 up top, which is a first degree polynomial, a linear polynomial, and down here in the denominator I have a second degree polynomial or a quadratic polynomial. When you put these two together in fraction form, you have what we call a rational expression or a rational function. Okay? So this is an example of a rational function. We also need to define the word asymptote. Okay? So let's take a second and do that. An asymptote is a vertical or horizontal boundary that most of the graph, if not all of the graph, does not cross. Let me say that again. An asymptote is a vertical or horizontal boundary that most, if not all, of the graph does not cross. Here's an example. Let me make this really big for you to see. Here's an example, okay? Now, these dotted lines are your asymptotes. Now, they're not really part of the graph, but we put them there so you can see that the graph does not cross these boundaries. Now, we're going to learn during this class period how to find these asymptotes, okay? So here's two vertical asymptotes, and then one of the asymptotes was horizontal. It fell right on top of the x-axis. Now, I know it looks like the graph right here is crossing the x-axis, but that's really a typo on their part. It's supposed to be a little bit lower. And what it means is this graph, as it curves and goes up, is getting closer and closer to 2. Right there, that number 2, but it's never going to quite be 2. And it's going to go up and up and up and get closer and closer to -4, where this vertical asymptote is, but it will never hit 4. And then also, notice how this graph here does the same thing. It's getting closer and closer to 0. This where the horizontal asymptote is. And it's getting closer and closer to -4 down here, but it's never going to touch or cross those asymptotes. So as you can imagine, students, It's very helpful to get these asymptotes drawn, because once you have these boundaries drawn and then you start plotting points, you can kind of see how the graph fits right in that little area right there, how it fits right there, and how it fits right there. And so asymptotes are very important, and once again, they are horizontal and vertical boundaries in which most of the graph, if not all of the graph, does not cross. Okay, let's continue on. So today we are going to learn how to find three different kinds of asymptotes. Okay, vertical, horizontal, and then a third type that we call slant or oblique asymptotes. Okay, you can write those down later. We're going to go through those one type at a time. Let's start off by learning how to find vertical asymptotes first. Okay, vertical asymptotes. Now, in order to find vertical asymptotes, this is so easy. You do one simple thing. Set the denominator equal to 0 and solve. It's that easy. Okay, let's practice doing this. Here's two problems. I want you to find the vertical asymptotes for this rational function right here. The vertical asymptotes. Well, all that you do is you take the denominator and you set it equal to 0 and you solve. It's just that easy. So I took the denominator, I set it equal to 0, and I solved. Now you should realize by now we have a quadratic equation, so we're going to try to factor. Notice my lead coefficient is 1. What two numbers when multiplied together equal a -8, but when added together equal +2? Well, that's going to be a +4 and a -2. If you multiply those, you'll get a -8, and if you combine them, you'll get a +2. So the factorization of this quadratic would be x plus 4, x minus 2. Now, we take each group and we set each group equal to 0 and we solve, and we get -4 for this group and we get +2 for this group. So there, you know what you just found? You just found the vertical asymptotes. So you would write them like this. You would say x equals -4 comma +2. There's your vertical asymptotes. So let me grab this picture down here. If I can get this right. And this is a picture of the last graph that we just looked at on the last page. And there we go. Do you see now how we have vertical asymptotes at where? -4 and +2. X equals -4. So we draw a vertical line going through -4. And x equals 2. So we draw a vertical dotted line. Your asymptotes should always be dotted, students. That way we know on the graph that the asymptotes are not really part of the graph. They're just boundaries for your graph. So there, look at that. You just found vertical asymptotes by very simply taking the denominator and setting it equal to 0 and solving. It's not that difficult, okay, students? It's really not. So with that in mind, let me go ahead and slide this out of the way. Let's try another problem, okay? Let's take this problem over here and let's find the vertical asymptotes for this function here, this rational function. Okay, remember what to do. Whenever I ask you to find the vertical asymptotes, you simply take the denominator and you set it equal to 0. So there, we've done that. Now we notice right away we have a third degree or a quartic equation. So I'm going to factor. Always pull out what's common first. I'm going to pull out an x, and I'm left with x squared minus 5. Easy enough. I pulled an x out of both terms. Now, if I take this group right here and set it equal to 0, I would simply get x equals 0. So there's one of my vertical asymptotes. Now, if I take this group right here and set it equal to 0 and solved, I would get positive negative square root of 5. Now, with the calculator, I'm going to get a decimal because I want to know where to put this on the x-axis. And so the square root of 5 rounded to one decimal place is 2.2. So really your vertical asymptotes would be x equals positive negative 2.2. So let's review. This is not difficult. In order to find the vertical asymptotes for this rational function right here, I simply took the denominator, which is right here, and I set it equal to 0 right here, and I solved. And after you solved, you see that you have 3 vertical asymptotes. Now I'm going to go ahead and create some space here so I can take a look at this graph very quickly. Let me pull my vertical asymptotes up here, out of the way. And let's pull this graph over here. So I've asked you to find the vertical asymptotes. We did that. Now, by the way, when I ask you to find the vertical asymptotes, you don't have to put them on a graph like I'm doing now. I just wanted to show you this so you see how all of this really does help you find the graph later. When we start graphing these functions, these boundaries are really helpful. Okay, so look at this. This is the graph of this function right here if we had graphed it. And look, we have a we have a vertical asymptote right here at 0, x equals 0. We have a vertical asymptote at negative 2.2 right here. And we have a vertical asymptote at positive 2.2. So there we go. You put those boundaries on your graph in the form of a dotted line, and that really helps you with your graph. Now, I'm not going to give you any more of these. You'll practice these in your homework, okay? But it's very simple to find the vertical asymptotes of a rational function, and here's the sentence right here. You set the denominator equal to 0, and you solve. It's that easy, okay? All right, let's continue on. Now, what about horizontal asymptotes? There are actually 2 scenarios in which a rational function has a horizontal asymptote. So please take some really good notes on this. Number 1, listen to this carefully. If the degree of the numerator is the same as the degree of the denominator, then a horizontal asymptote exists at y equals lead coefficient over lead coefficient. Now I'll explain this later, okay? But that's the first scenario. Scenario number 2. If the degree of the numerator is less than the degree of the denominator, then you automatically have no work to do. You know that a horizontal asymptote exists at y equals 0. Now this is not hard as long as you'll memorize this, men. It's not that hard, okay? Let's look at one example for both of these cases. All right, here we go. Let's start off with this example here. I want you to find the horizontal asymptotes for this function, okay? Here we go. The degree in the numerator is 4. And the degree in the denominator is 4. So notice whenever the degrees are the same, you definitely have a horizontal asymptote. And let me pause. By the way, sometimes you won't have any vertical asymptotes. Sometimes you won't have any horizontal asymptotes, okay? But in this case, because the degree in the numerator right here, 4, matched the degree in the denominator, 4, then you know you have a horizontal asymptote. And here it is. It exists at lead coefficient over lead coefficient, y equals. So you would put y equals. Now, what is your lead coefficient up top? Negative 7. What is your lead coefficient in your denominator? Positive 11. Isn't that easy? So your horizontal asymptote, a negative divided by a positive is a negative 7/11. So your horizontal asymptote for this function here is y equals negative 7/11. Now, the book did not give us a graph for this, so I typed it in my graphing calculator and took a picture of it, and here's what it would look like. Now, the graphing calculator doesn't do a very good job. It does okay. But if you'll notice, it's really hard to see, but you have a horizontal asymptote. I'll try to draw it on here, draw it on here for you. Horizontal means it goes across this way, left to right, and it's going to take place at negative 7/11. So y equals negative 7/11. So if you look, you can see there's a line, a horizontal asymptote going right through here, right below the x-axis, and it's at negative 7/11. And by the way, I know this graph looks a little confusing, but let me go ahead and just kind of draw it for you. I'll put the graph in red. The graph is going like this and curving down like this, okay? And so there is a horizontal asymptote right here. I'm not sure exactly where it is, but it's right here. There's another horizontal asymptote right here. I'm not sure exactly where it is, but it's right here. And then the graph is going like this. And you're probably saying, Mr. Earhart, you really got good eyes to see this. Well, I just know what it does from experience. Now, here's what I wanted to show you. Remember how I told you earlier in the lesson today that sometimes graphs will cross an asymptote occasionally? Well, please listen to this. I should have put this in a sentence for you to write down. Graphs will never cross vertical asymptotes, but sometimes they'll cross horizontal asymptotes. So the graph, even though you can't see it, it's kind of going like this and then like this. So notice there's one small part of the graph right here that crosses the horizontal asymptote right here. So occasionally horizontal asymptotes will be crossed, okay? Vertical asymptotes will never be crossed. But let's not lose sight of the trees for the forest here. All that I'm trying to teach you here is how to find the horizontal asymptote. And so when the degree in the numerator matches the degree in the denominator, you will have a horizontal asymptote, and it will take place at the top lead coefficient over the bottom lead coefficient. So your horizontal asymptote took place at negative 7/11. Now, you can see that green line right here, barely below the x-axis. And by the way, if you take 7 and divide it by 11, you'll get 0.63. And that looks just about right. Our green line right here going left to right, your horizontal asymptote, is about at negative 0.63. Okay, so I hope that makes sense. If not, back it up and watch it again. But the way you find a horizontal asymptote when the degrees match in the numerator and the denominator is you put the top lead coefficient over the bottom lead coefficient. Okay, let's take a look at this next problem. All right, let's go ahead and slide this problem over here real quick, students. Let's take a look at this one. All right, here we go. Now, notice that the degree in the numerator is a degree of 1. There's a 1 here for the exponent, and a degree of 3. Notice the degree up top is less than the degree in the bottom. So look at number 2. If the degree in the numerator is less than the degree in the denominator, then a horizontal asymptote exists at y equals 0. So let's take a look at this graph. Now this graph's really hard to see. It's much worse than the other one, but it still gives us a little bit of a picture, so we're going to use it. And I can explain later why it's so hard. The graph itself is doing something like this. It's coming, it's hitting here, it's peaking, then it comes back down, then it goes back up to here, then it comes back down and flattens out, and it gets closer and closer to the x-axis, but it never touches it. And you know why? Because you have a horizontal asymptote at 0. So you draw a horizontal asymptote right through 0. Now really we should do it in a dotted line, but you get the point. You have a horizontal asymptote going right through 0 on the y-axis. So actually it falls right on top of the x-axis. So there's your horizontal asymptote. Okay, now I'm not going to give you any more of these. You're smart students. Matthew, Caleb, you guys know what you're doing. You're going to practice on your homework tonight. But my point is make sure you understand what I'm saying here. There are 2 scenarios in which you have horizontal asymptotes. Okay, all right, we have one more case to look at. And these asymptotes are called slant or oblique asymptotes. I call them slant asymptotes. The book calls them oblique asymptotes. Either way, it's the same thing. All right. Now, this will not make a lot of sense, but after I explain this to you and then show you what to do, you will understand it. A slant asymptote exists when, are you ready? Here it is. When the degree of the numerator is exactly 1 degree higher than the degree of the denominator. When this happens, you use long division to divide out the fraction. The quotient will be the linear equation of the slant asymptote. Now that probably sounds like Greek, and that's fine. Let me help you, okay? This one here, slant asymptotes, is a little tougher than the other ones, so let me give you an example. Here it is. Now let me show you what to do. Let's say you're taking a test or a quiz, and I've asked you to find the slant asymptote. Well, first of all, you look. If the degree in the numerator is not exactly 1 more than the denominator, then you would say no slant asymptote exists. However, the degree up top is 2 and the degree in the denominator is 1. So the degree up top is exactly 1 more than the one on the bottom. So we know we have a slant asymptote. Now here's what you do. You use long division to divide out this fraction right here. So we're going to use long division. X minus 2, 2x squared minus 3x minus 1. Now remember what to do. Divide first term into first term, and you would get 2x. 2x times x is 2x squared. 2x times negative 2 is negative 4x. Now we subtract. 2 minus 2 is 0. Negative 3, now watch your signs, minus a negative 4 would be a positive 4. So a negative 3 and a positive 4 is a 1x. Bring down your negative 1. X goes into x 1 time. 1 times x is x. 1 times negative 2 is negative 2. We subtract 1 minus 1. These cancel out. Negative 1 minus a negative 2 is 1 plus 2, and that's 1. So we have a remainder of 1. I'm just going to put RY. I know we don't usually do that, but there is a reason I'm doing that. Now, if you'll look up here, I say the quotient will be the linear equation of the slant asymptote. Let's just stop for a second. Okay, let's review. Was the numerator 1 degree higher than the denominator? Yes. Did I use long division to divide out the fraction? Yes. Here's your quotient. Forget the remainder. We don't care if there's a remainder or not. We're not going to use it. You take your quotient, 2x plus 1, and you set it equal to y. So we say y equals 2x plus 1. Mr. Earhart, why do you set it equal to 1? Because it's going to represent a linear equation. And that linear equation is your slant asymptote. So I divided out my fraction, I got my quotient, and then you always set it equal to y, and that's going to be your slant asymptote. Now let's take a look at the slant asymptote. Mr. Earhart, this is my slant asymptote right here, this thing. Well, sure it is, definitely. If I asked you to graph that line, could you not graph it really quick, guys? Could you not just very quickly put a 0 in for x and put a 2 in for x? Put a 0 in for x, you'll get out of 1. Put a 2 in for x, you'll get out of 5. So you would go to 0, 1, that's right here, and 2, 5, put a point here, and draw your line. So you know what you just drew right there? You just drew the slant asymptote. The only thing you got to remember is it has to be dotted. So there's your slant asymptote. Isn't that easy? All you did was you use long division, and the quotient is set equal to y, and then you graph that line. So there's your slant asymptote right there. Y equals 2x plus 1. We know how to graph these linear equations. Those are the easiest graphs we've ever done this year. And so there's your slant asymptote. Now, let me go ahead and erase this and pull up the actual graph of this rational function. Doesn't that look like the exact same dotted line that I just drew? Sure it does. Look at that. It's going right through 0, 1. It should go through 2, 5. 1, 2, 3, 4, 5. Yep, right there. 2, 5. Look at that. There we go. So there's your slant asymptote right there. Of course, you wouldn't use a dotted line, but I'm trying to show you there's your slant asymptote. And by the way, if you would have found your vertical asymptotes for this, you would have seen you have a vertical asymptote right at 2. So if I asked you to graph this, which is what we're going to do tomorrow, you would see that you have 2 asymptotes like this intersecting. And so you know one graph takes place here in between the two, and we'll get into that tomorrow how we do that. And then here's a graph right here taking place in between the 2 asymptotes. And that's it. Guys, I'm telling you, this is not too difficult if you'll just learn how to find the slant asymptotes. Okay, so there we go. No more examples of these. You guys know how to do these. Now you need to practice on your homework. Okay, let's very quickly take just a second and let's quickly review these scenarios. Let me scroll back up here. Horizontal, vertical asymptotes. You do one thing, set the denominator equal to 0 and solve. That's how you find your vertical asymptotes. Horizontal asymptotes, if the degree is the same in the top as the bottom, you put lead coefficient over lead coefficient. If the degree of the numerator is less than the denominator, then you have a horizontal asymptote at y equals 0. And I should have covered this. What if the degree is higher in the numerator than the denominator? Then there's no horizontal asymptote. You don't have one, okay? You have to have one of these 2 scenarios in order to have a horizontal asymptote. So if you don't have one of these scenarios, then there's no horizontal asymptote. And then lastly, for the vertical or for the slant asymptote, you simply must have the degree in the numerator must be exactly 1 more than the denominator, and then use long division, divide it out, get your linear equation, and then graph that linear equation, and that'll be a slant asymptote. Okay, well, here's your homework, page 316, numbers 1 through 25 odd. Please go ahead and get started on that. Call or email if you have any questions, and hope you guys have a good day today.